So as we get into module 5.2 for ME144 heat transfer, we're continuing looking at one-dimensional steady-state conduction, but now we're going to consider thermal energy generation. In previous section, we looked at the same 1D steady-state conduction, but without the thermal energy generation. So how does this affect our governing equations and how we go about our procedure for analysis for solving some of these problems? Well, we want to consider the additional effects of this temperature distribution of process that may be occurring within the medium now. So in particular, we'll consider situations for which thermal energy is being generated due to conversion from one form to another form of energy. So within this module here, we're going to take a look again at our plane walls and radial systems, but now add in that thermal heat generation. What does that mean for our key equations and governing equations? How about our tabulated solutions and our procedure for analysis from there? Take a look at some practical applications, and then go through a couple of hand solutions to some different problems. So this module is going to relate to Chapter 3 in our textbook, and particularly looking at Section 3.5 and Appendix C in the back of your book. So as we look at this 1D steady-state conduction with this thermal energy generation, we're going to see, okay, what are our governing equations? And a lot of what we're going to look at here for the governing equations, variables, and values is some reference tables, as well as some reference equation charts as well that we'll be utilizing for when we're solving these problems. So as we start discussing some of these charts and tables that we're going to look at here, I want to reference back to table 3.3 in our textbook here. And this is for one-dimensional steady-state solutions to the heat equation with no generation right there. So we see this for a couple different things. We see this for the plane wall, cylindrical wall, and our spherical wall. Now for each of these situations, we have our heat equation, our temperature distribution, heat flux, heat rate, and thermal resistance. So I think this is a great chart or table that we can reference back to for saying, okay, I want the heat equation for this compared to this, or I need the temperature distribution for these situations. It's all in one area that we can reference back to. So that's why I wanted to include this in this presentation, this module here, so you have a spot that you can go back and reference this if you're looking for these governing equations as you're solving through a problem. And this is where it's great to have these, especially once you've created that setup page. And you know, okay, I have this information they've given to me in the problem. I have all this information that they've asked me to solve for. What governing equation am I going to go for? Like, okay, when I give information, they say I'm looking for my heat flux, and it's for a cylindrical wall right there. So therefore, I can come over here and go, okay, come across, come down here. Okay, that's what my governing equation is. Okay, they gave me a delta T, and they gave me the L in the problem statement, but I didn't really see where this R1 is. How do I go about solving for that there? Something like that. Or maybe they gave you the material properties and you need to go look up your K value. But having that information in your setup page is really going to be very beneficial. So when you come to a nice organized table like this, you can kind of pick and choose which ones based upon that given information what they're asking you to solve for. Also, thing to note, as you're looking at these tables, don't just look at the governing equations up here, but look down here for any of the other notes. So some of that stuff that's missing down here may be given in some of these other equations, and it might be slightly different for a sphere versus a cylinder right there, especially right here if we're talking about our critical radius right here. If we're dealing for a cylinder, we have this relationship here. We can plug in for our RCR right there, and if over here our critical radius for a sphere is going to be 2K over H right there. So pay attention to the little side notes, or if there's any notes in the top as well in some of these charts, those can be very important. So now let's jump into this implications of our energy generation. So what this is going to involve is a local volumetric source of thermal energy due to conversion from one form to another form of energy in a conducting medium. Now the source may be uniformly distributed, as in when we take a look at the conversion from electrical to thermal energy. And if we're doing that conversion from electrical to thermal energy right there, this is also known as ohmic heating. So again, when you're reading through the problem statements, whether it's for an exam, quiz, sample problem, homework, whatever it is, take a look at these key words and said, okay, in this problem we have some ohmic heating. Well, therefore you know you're going to have to do that conversion from electrical to get to your thermal energy with that there. And what are your governing equations? What are your units you should be looking at? What other things should you be looking for to solve for? So all of that right there, pay attention to how things are worded for keywords and key phrases in your problem statement. Now, if we're talking about the rate of energy generation per unit volume again, this is where we have our Q dot right there. So we have this over here from our governing equation here at 3.43 back in our textbook, that our Q dot right here, this rate of energy generation per unit volume, is equal to our E sub G dot over our volume right there. So our E sub G is the rate of energy generation in units of watts right there, divided by our volume right there. Well, then if we want to go to electrical right there, we recall this relationship here where we have I squared times our RE, where I is the current and E is the electrical resistance. So this is kind of that conversion that we're talking about right there from electrical to our thermal energy right there by this relationship given by equation 3.43 in our textbook. Now, it may be the case that this is non-uniformly distributed, as in the instance of absorption of radiation passing through a semi-transparent medium. For a plane wall, we have this relationship right here. We have this equation down here where our Q dot right there, or our rate of energy generation per unit volume, is proportional, so that's what the symbol right here is proportional to e to the negative alpha x, where our alpha is the absorptivity right there. So that's our following relationship there for this non-uniform distribution, in particular for a plane wall. Now, the generation affects the temperature distribution in the medium and causes the heat rate to vary with location. So location does become important right there, and it is going to vary based upon where it is, thereby precluding inclusion of the medium in the thermal circuit. Now, as I mentioned, a lot of this module, I'm going to be referencing some of these tables and charts in the appendices and some diagrams here. So one of the things I said we're going to be taking a look at within this module is our Appendix C in the back of the book. So this is important. It's a great reference for you guys to get used to and know where things are, especially if you're starting to solve some of these problems for homeworks, exams, or even practice problems there. So we looked at table 3.3 when we were talking about without generation, and we talked about those three different scenarios that we looked at previously of the plane wall, the cylindrical wall, and the spherical wall. So what's good about this chart here, or this image here from Appendix C, is a clear representation of all three of these geometries and the associated variables with those. So if we take a look at the simple case, we usually like to start with that plane wall. It's easy to visualize. Simple case here, a lot of times it's just 1D right there. You're looking at it, okay, there is my TS1, a temperature at surface 1. There's my center line right here. Here's a negative L distance away and a positive L distance away based upon X being positive going to the right there. There's my Q dot right there. And then over here on the side, I have my surface temperature at surface number 2 over there. So I can see how things are labeled and how they're laid out, and that's just simply for our plane wall. So this is all for, if we look at this here, this is one-dimensional conduction, systems with uniform thermal energy generation. We have a plane wall right here that we just looked at with asymmetric surface conditions. Then we also now we're going to look at our cylindrical wall and the spherical shell. So when we look at the cylindrical wall over here, what do we see? Well, now we have this length L over here. We still have the center axis right here going all the way through this guy right there. And we can see based off that center axis, we have our R1 as we go out to the inner layer right there, the inner radius right there. And our R2, we come out here. That's our outer radius, the outside radius of our cylindrical wall right there. And then you can see on the outside radius at R2, we have this TS2, our temperature at surface 2, whereas surface 1 is the inside temperature at our distance of R1 off that center right there. And through our actual material right there, there's our Q dot right there. So that's the general terms, general variables, and how everything relates for this cylindrical wall. So last, we're going to move on to our spherical wall over here. And we can see we have this representation here, just a kind of slice down through the center of it as a bird's eye view of it, if you will. And we can see, oh, there's our center right there. Okay, then we come out to our first surface right there at a distance of our R1. We go out there on R1 on that surface. That's our inner surface right there, our inner radius of the sphere. This is our TS1, so that whole encompassing sphere in 3D, as we visualize it that way, is our TS1 surface there. And then we go out to our outside surface right here. This is our R2 on our outer surface right there, and we can see at that outer surface we have the temperature there, our outer surface of TS2, and then within the material itself there's our Q dot. So this is a great comparison in this Appendix C right here within figure C1 of the plane wall, cylindrical wall, and our spherical wall, and how our variables relate, where those surface temperatures are, where our Q dot is, what these values actually mean. So this is a great one to reference if you're dealing with any of these three types of problems within your homework, exams, or practice problems. So at the beginning of this lecture, we looked at table 3.3 from our textbook in chapter 3, and we had a couple of equations for our plane wall, cylindrical wall, and spherical wall for 1D steady state conduction with no generation. Well, let's take a look now. If we go to table C3 in the back of our textbook and our appendices there, what we have here is that one-dimensional steady state solutions to the heat equation for plane, cylindrical, and spherical walls, but now with our uniform generation and asymmetrical surface conditions right here. So now what we can see, if we go here, if we want our temperature distribution equations for either a plane wall, cylindrical wall, or spherical wall, we can reference these equations C1, C2, and C3. Then we can go on if we want our heat flux equation over here for our plane wall, cylindrical wall, and spherical wall again right here. We can reference back to C4, C5, and C6 within this here. And you see these are rather complicated, not something that's easy to memorize or even easy to derive. But knowing where you can go to get these equations in the back in this table C1 becomes very useful, again, with that same setup page. And you know I have this, this, and this. I'm looking for this and this. This is my shape I have. These are my conditions I have. You can go through and find the appropriate equation that way there. We have the same thing again down here for C7, C8, and C9, but now for our heat rate equation here for that same plane wall, cylindrical wall, and our spherical wall. So as we go to the back appendice in our book right here, we take a look at table C2. What we have here is the alternative surface conditions and energy balances for one-dimensional steady-state solutions to our heat equation for our plane, cylindrical, and spherical walls with the uniform generation. Now what I've also included here on this slide are the plane wall, cylindrical wall, and spherical wall diagrams that we saw previously in this module there with all their associated variables. And where this becomes important is we're taking a look at these governor equations. Let's, for example, take a look at our plane wall. Well, now we know we're looking at this diagram right here. And it tells us at x equals L, our heat flux of Q double dash S1, surface 1 right there, is equal to negative Q dot L. So we're talking over here, there's our x equals negative L, there's our surface right there we're dealing with, so that's our L value right there, minus our K, which may be given to us our problem, all over our 2L right there, there's our L value again there, times our temperature difference between TS1 and TS2, so there's our surface temperature, so it's the difference between those two temperatures. Then I can also say, okay, when x is equal to L, okay, now I'm over on this surface over here right there. Well, my heat flux there is equal to now Q dot L. You can notice the sign change in our convention right there, minus our K over 2L times TS2 minus TS1, that temperature difference there. So it's easy for us to look at those governing equations, go over to our diagram and relate back. We can do the same thing for our cylindrical wall. We're looking, okay, what is R1? Oh, that's my R1 right there. Okay, what is my TS2? There's my TS2. And we can relate this to whatever the problem is that we have there and know what variable names we should use, how these relate back to these equations here, where we can plug in. Then we can look at, again, in our setup page, what we have, what we're given, and what we're looking to find in that problem there. So all that information becomes very useful, and these two charts, these two tables tie in very well together, where you're looking at all your governing equations based upon, okay, I'm dealing with a spherical wall, I'm dealing with a cylindrical wall, I'm dealing with a plane wall. Okay, what am I looking for? I'm looking for uniform surface heat flux right here, and I know this and this and this, but I don't know that. How does it relate to my diagram? So that's really, really useful as you're going through the problems to be able to quickly flip back to these tables and look at it kind of in general form for the equations and a really general diagram. Because without these, you might be just going back to previous problems or example problems in the book or homework problems that aren't quite the same or have different variables, or some are given as numeric values and you don't know the variable name. So going back to the C2 table there and referencing back to these diagrams that we saw earlier can really at least help you get started and know where to go from there. Give you that governing equation, help you with the visualization, and know how to begin the solution to your problem. So now as we move on to table C3 in our appendices right here, we're still dealing with our 1D steady state solutions to the heat equation for uniform heat generation, but now we're doing it for a plane wall with one adiabatic surface, a solid cylinder, and a solid sphere. So that's going to change things a little bit here. And what we have over here in figure C2 is we have these uniform one-dimensional systems with this, the plane wall with adiabatic surface, the solid cylinder, and the sphere, showing for each of these. If we take a look at our plane wall here with the one adiabatic surface, this is what our initial diagram, our general diagram, is going to look like for this here. You say there's our x going over in this direction. Here's our distance L over here at this surface right here. There's our surface temperature T sub S. So you can see it's a little bit simplified down. We're dealing with only the one adiabatic surface right there, and there's our Q dot there. The same for a solid cylinder. We don't no longer have that inner shell right there or inner wall. It's a solid cylinder. So we're not dealing with a plane wall, a cylinder wall, and a sphere wall. We're dealing with a solid wall right here with the one surface, a solid cylinder, and a solid sphere right there, which simplifies it down. So with the cylinder, we take a look here. We just have this outer surface temperature there and the one outer radius R naught there. Same for our solid sphere. There's our outer radius right there, R naught, and there's our outer surface temperature, our TS1. There's our Q dots at the inside of the whole material because it's now solid. So with that there, we can see for each of these, the plane wall, circular rod, and circular sphere, for those solid ones there, we have our general equations for temperature distribution in C22 through C24. We have our heat flux general equations, C25 through C27, and we have the heat rate equations here in C28 through C30. If we look at these here, they're simplified down now. So just take a look at the temperature distribution for a plane wall. So our T of X, our temperature distribution, the X direction here, okay, there's our X direction going in that way over here, is equal to our Q dot, well, there's our Q dot right there, times our L squared right there, there's our L right there, all over 2K, we'll get the K from material properties, okay, 1 minus our X squared over that same L squared right there, okay, and there's our X direction again there, plus our TS, there's our TS right there. So it's great again to have this diagram to go with this table 3. But what we want to pay attention to is when we're going back to these tables that we're utilizing the right diagrams with the right equations. So we're paying attention. This is just for, like we said here, plane wall with 180 back surface, solid cylinder, solid sphere. So if they have a wall to them there and it's not solid like that, we need to go back to table C2 and our other diagrams. If we're dealing with this one right here, we need to look at these diagrams here. So this again, if you're reading through your problem statement, you're looking at it, you know, what am I dealing with? Do they physically show me a diagram? Do they tell me it's solid? Do they say it's hollow? Do they say there's a wall thickness? All of those things are kind of keywords and key phrases that we should be looking for to determine which of these charts we're going to go to, which of these tables we're going to look back at to get our governing equations. And then at the same time, are we looking for heat rate? Are we looking for heat flux? Are we looking for temperature distribution? And make sure we plug into that, figure out what we know, what we don't know. For what we don't know, do we have a way to solve it? Do we have another governing equation or relationship we can use to solve for that? So now we'll move on to the next table, back in our appendices, Appendix C right here, and this is table C4. Now what we have here is alternative surface conditions and energy balances for the same 1D steady state solutions to the heat equation for uniform generation and that same plane wall with the 180 adiabatic surface, the solid cylinder, solid sphere, so those same diagrams that we saw on the previous slide there. Now this is for the prescribed transport coefficient and ambient temperature. So for the plane wall, we have the relationship here in C31 right here, where when X is equal to L on that diagram there, we have that Q dot times L is equal to U, which we can go back again. What did U? We can figure that relationship out back in that chapter again that we looked at earlier, times that temperature difference between our TS and our T infinity. So this gives us a general governing equation. Like I said, when we don't know the value for something like that, or we know that there's another equation we need to, this gives us a starting off point with a general governing equation that we can then go back and fill in the blanks for there. It's the same thing for that circular rod. Again, R is equal to R outer, and for the sphere, R is equal to R outer as well, because these are solid cylinder and a solid sphere right there. And there's our temperature differences right there. And temperature difference you see is our surface temperature and the surrounding, that ambient temperature T sub infinity right there. So these are our governing equations again now for these 3 conditions right there for the plane wall, solid cylinder, and solid sphere. So now let's take a look at a general example here of a plane wall. Now they tell us here in this example that we have a one-dimensional steady state conduction. So we're only dealing with conduction right now in a plane wall of a constant K value right there. So that's going to simplify it down. Uniform generation and asymmetric surface conditions. So based upon all the information, we go back to one of those appendices. We go into our textbook, into that same chapter, look through those sections, come up with our governing equation. What we do is we find for our heat equation here, back in our textbook, this is equation 3.44. We have our diagram over here. Okay, here's our X positive to the right, here's our L positive there, negative L there, surface temperature 1, surface temperature 2, and our Q dot value right there. So we have this equation here, d over dx is our K, and they tell us that's a constant K right there, times dt dx, our change in temperature with respect to X as we're coming out from our X over here, plus our Q dot, well there's our Q dot term right there, let's give it to us in diagram, is equal to 0. We can simplify this down. Okay, now this is equal to second derivative with respect to X of our temperature right there. So d squared T over dx squared, plus now we have our Q dot over K right there is equal to 0. And again, this comes from equation 3.44 in our textbook. Now for our general solution to this right here, what we have is from 3.45 in our textbook right there. Our general solution would say, so we solve this for T of X right here, do all this little math right here, calculus. Well, let's see d squared t, a second derivative of temperature with respect to its position right there in the x direction, is a double derivative. So we did take the integral twice, two integrals of that right there. And when we see that, we do that, we can back out our tx right there. And we could do out that integral, or we could take a look at our general solution right here and see that this is equal to our negative q over 2k times our x squared plus our constant c1 times x plus our constant c2. And again, this relates back to equation 3.45 in our textbook. So as we continue on with our plane wall here, we're going to take a look at conduction with uniform heat generation. So we're going to look at that for a symmetrical boundary conditions and adiabatic surface at a midplane right there. So if we're talking about symmetric surface conditions right here, as in the top at part B right here, we want to find our temperature gradient at the center line. So our center line right there goes right down through, and that's our T naught there. But if we're talking about it for our adiabatic surface at a midplane right here, we may be looking at the insulated surface. So we come down here and we can see that same line right there is right at our insulated surface right there, and there's our T naught there. Now we also may want to be taking a look at the magnitude of our temperature gradient as we go out away from that line of our L there. So we go out away from in our x direction over here. So if we're talking about our temperature distribution right here, our T of x, our temperature relative to our distance away from that T naught there of our midline there, so we're moving out, is equal to this relationship right here shown in equation 3.47 in our textbook there, where we have our Q dot times our L squared right there. Okay, there's our L value right there as we're moving out in the positive x direction there, all divided by our 2K, which is our K is going to be our thermal conductivity constant right there, which is going to be a lookup value for our material, times our 1 minus our x squared over L squared right there. So again, there's our L as we're moving out in our x direction there, plus our surface temperature, our T sub s right there. So this again relates back to our 3.47. Then we may have to ask ourselves, how do we determine this TS right there? Is it something that's given to us in the problem statement? We need to find another way to calculate that as well based upon which problem we're solving. Now, if we're talking about the overall energy balance on the wall, we have our governing equation down here. We have our negative E dot out plus our stored energy E dot G right there is equal to 0. So we've seen this equation before, so we can still utilize that there. Plug in for our specific equation. We have our negative H times our AS times our temperature difference between our surface and our ambient right there. So again, now if we're dealing with convection terms over here, we have both of those that come into play right there. That's where our H term comes from right there. Plus our Q dot times our A sub s for our area right there, times that length L, depending on where we are along our x-axis right there, is equal to 0. And we can simplify this down now here. We have our governing equation in 3.51 in our textbook right there, where our TS, our surface temperature, is equal to that surrounding temperature right there, our T infinity, plus our Q dot times that distance L over our H value there. So we can plug that in. So that may be one way that we can solve for that TS right there if we need to do for our equation right there. So that's TS, or our surface temperature, may be dependent upon convection terms from our outside fluid, submergent, or air, whatever it may be. So as we continue on with our radial systems here, we've been looking at two different types, our cylinder and our sphere. Now with the cylinder, we had two different types here. We had our cylinder wall, or our tube, and our solid cylinder, or our circular rod. Then we also had for our sphere, we had the spherical wall, or a shell, and our solid sphere right there. Now as we're taking a look at our heat equations for each of those different types right here, for cylindrical, what we're looking at is 1 over r d dr times our kr, constant k right there, times that radius r right there, times our dTdr, our change in temperature with respect to that radius moving out there. And we can see if we start at the center and we move out, there's our radius there. Start in the center and move out, there's our radius there. Plus our Q dot, and there's our Q dot and our Q dot there. And this is equal to 0. Now for our spherical over here, what we have now is we have 1 over r squared. So we can now see that this is a squared term. It's just squared to 1 over r. It's still ddr. Then we have a kr squared again there as compared just to our regular r there, over dt dr plus our q dot is equal to 0. And again, there's our radius coming out there. There's our radius coming out from the center over there. And then we have our Q dot term right there and our Q dot term right there. So the only real difference between cylindrical and spherical is this R squared term that we're seeing right there at the beginning. And we're seeing again right here for the spherical versus our cylindrical. So as we continue on to the radial systems right here, we want to take a look at our solution for a uniform generation in a solid sphere of constant K with convection cooling. This is a rather specific problem right here. Before this here, we can come up with our temperature distribution relationship. We can see our following relationships here. We can start up here with our K times R squared times our change in temperature with respect to that distance along the R right there is equal to our Q dot times R to the third divided by 3 plus our constant right there, C1. Then we come down here and solve for T, and we can do another set of integration on that to get this here, and we can rearrange this, and we have our C1, our C2. Then we come through and say, okay, well, our temperature distribution, our change in temperature with respect to dr when r is equal to 0 is equal to 0, so therefore we can solve for our C1. Our C1 becomes 0. Plug back in over here, and we get this relationship there. Keep going through this, derive it, and we end up with this relationship down at the bottom here, where our T of R is equal to our Q dot times our R naught squared all over 6K times 1 minus our ratio here of R squared over R naught squared right there, plus our surface temperature TS right there. Well, how do we get up to this surface temperature right there? There's two different ways. We could use our overall energy balance right here, our negative E dot out plus our stored E dot G, E sub G dot right there is equal to 0. We can solve now our T sub S is equal to T infinity time, or plus our Q dot times R naught over 3H right there. Or from our surface energy balance, we can come up with that same relationship right there where we're taking a look at right here, our E dot in minus E dot out is equal to 0 right there. We have our conduction and our convection term right there. Plug in, we end up with the same relationship there for our TS. Now, a summary of this temperature distribution is also provided again back in that appendix C right there for plane, cylindrical, and spherical walls right there, as well as the solid cylinders and spheres right there. So this is just one specific case. So you can go back to that appendices C again that we already took a look at earlier to get all those general equations. You don't have to worry about going through all these derivations there. We can go back and look at those for those specific cases. Now note how the boundary conditions are specified and how they are used to obtain the surface temperatures right there. So that's something that is going to be important. You need to pay attention to within your problem statement and your initial given diagrams.